Alright, today we're going to talk about Chapter 9, Basic Circuit Analysis and Passive Components. The objectives of this chapter are to recall your basic rules of circuit analysis and methods, understand the behaviors of the most commonly used passive components, understand the practical and physical aspects of resistors, capacitors, and measuring instruments, and develop analytical skills and physical intuition necessary to be able to effectively use the most common electronic components in ICs. We're going to start off with voltage, current, and power. In electrical engineering, we focus on current flow. Even though this is the hypothetical movement of positively charged particles. Let's start with some definitions, like usual. First we have charge, which is shown with a Q, and its unit is the coulomb. Which is C, big C. This is the quantity of charged particles. Then we have current, or I. The unit is the ampere, or A, and it is the number of charged particles that move past a point in a given amount of time. This is dq, or our charge, dt. Usually we measure this in milliamps or microamps. If you have a full amp, that's a lot. Then we have potential. If you can think of it like potential energy, like we have in physics. This is when current flows in response to externally applied electric field. This is when work is done. Then we have voltage, which is the strength of the electric field. The unit for voltage is V, which is also known as the work per unit charge, dW dQ. Usually we work in the range of microvolts to tens of volts. This is not absolute. So when you measure voltage, you have to measure it across something. It's a relative quantity. So anytime you're using a voltmeter or an oscilloscope to measure voltage, you have to have two leads. One usually goes to ground, but it doesn't have to. and that's where you are looking at the voltage across something. Then we have power, which is the rate at which work is being done. So power is equal to work over time, which is joules per second, which can also be joules per coulomb times coulomb per second, which is equal to V times I. So when we're using, when we're in electrical stuff, our power is voltage times current. I really like to use this analogy. It's a good one. It talks about it in your book. But you can compare what happens with our electrical circuits to a hydraulic system. So if you're thinking about current flow in our electrical system, that is like the flow of water in a pipe. So if our electricity flows in response to a change in voltage, our fluid, or water, flows in response to pressure. If we have a conductor in our electrical system, this can be analogous to a pipe in our fluid system. Our voltage, then, we reference ground in our electrical system. In our fluid system, we have pressure, and we reference atmospheric pressure. And then if we have a voltage source in our electrical system, that is analogous to a pump or column, where we create potential energy. We have a number of sources for voltage. First, we can use a battery, which is an electrochemical cell. This is the most common one we will be using, but we can also use power supplies. There are signal generators, something like a they're kind of like power supplies, but they can be put in racks like your oscilloscopes. Sensors can also create voltage. And then an ideal voltage source would have constant voltage irrespective of the current that you have. These are the symbols that you would see for these different types of voltage sources in your current diagrams. We have two kinds of voltages that we work with. We have DC current, which is when you have a constant voltage of single polarity, and alternating current, when you have voltage that varies with time. It may either go positive to negative or positive to 0 or something like that. Then we can also have current sources. Well, not really. These are ideal, so you might see them in a circuit diagram or when you're analyzing your circuits. It's when you put this in your circuit and it will produce whatever voltage you need to have a constant current, but it doesn't actually exist in real life. Alright, so let's talk about circuits and ground. A lot of people get nervous when we talk about ground. Anyway, okay, so we have several different types of circuits shown here. First, we have a complete circuit. So which one is the complete circuit? this is our complete circuit. We have voltage and current going around with a load and a voltage source. Then has path from one terminal of the source here around to the other terminal of the source. Then we have an open circuit which has a broken path, so it does not have current flow. And then we have a short circuit where you have your straight path between terminals. This is, if it's a passive device that you have in here as your load, then it doesn't do anything, no effect. But if you have it across your voltage source, then it's damaging. So you want to be careful not to short your circuits. This happens a lot, which is why we have our fried Arduinos. Then we have ground. Ground is just what we use as our zero reference point. This is used a lot when you're looking at voltage because, again, if you remember, voltage has to be is across something, so it's a comparison. So a lot of times we'll ground it. This is how it's shown in a schematic. You can show it either one of these two, A or B. It's shown with these three little lines here. Yeah, or these are the other ways. Most of the time we're using earth ground. So if you're grounding something, like you're using your oscilloscope, you either need to connect, I highly recommend if you're using like an Arduino or a breadboard and looking at it with your oscilloscope, to connect it to a ground pin or something on your Arduino. But if you're doing different types of circuits in real life, you can actually connect this to something that's grounded on the earth. So this is, both of these are showing the same thing. A and B are the same, they just look a little bit different, but they're both equally correct. Alright, now we have our laws of electronics. First we have Kirchhoff's first law, which is the current law, or KCL. This is where the sum of all the current entering a node of a circuit is the same as the sum of all the current leaving that same node. Also known as conservation of charge. So all of the current going into a node is the same as the current leaving the node. So if you have a node, you have current coming in and current going out. In this simple case, I1 has to equal I2. Or you could have another one, I3. All of those that are going in have to equal what's going out. Then we have Kirchhoff's second law, or KVL, the voltage law, and this is where the sum of the voltage differences about any closed loop in a circuit is equal to 0. This is also, so this is the where the sum of all of the voltages around a loop are equal to 0. So this is the conservation of voltage. Alright, next we'll talk about resistance, and we can use the analogy that we have water flowing through a pipe